third one, third modulus, that is modulus of rigidity. Modulus of rigidity, and the symbol used, some books used n, some books used with this symbol eta. Okay, so we are using this eta. The symbol is eta, eta, Greek symbol called as eta, not n. Some books use this to be n, doesn't matter. आता या केस मध्ये first we'll write the definition. It is defined as, it is defined as, it is defined as the ratio of, it is defined as the ratio of the tangential, TANGENTIAL. I don't know how many of you know this word, meaning of this word tangential. Tangential stress to shearing strain, SHEARING, shearing strain. Okay, we'll complete. आपण हे बघूया काय याचा अर्थ काय होतो. What is tangential stress and what is tangential strain? Okay, for that now let's draw a simple diagram. आपण एक छोटीशी diagram काढूया. That will tell you something very interesting. Okay, so draw one cube of certain size, certain dimensions as shown by this. So this is the cube. So कुठलाही एखादा diagram काढा which is found to be of this nature. This is the cube, and here I am connecting this sides also. Okay, माझ्या diagrams एवढे फार चांगले असत नाहीत. I am not that expert in drawing this diagram. Doesn't matter. Well, we have to understand this. Now, length of this is L, and this is said to be fixed. This is said to be fixed. Your fixed base. And now apply force. Okay, ढकललं म्हणजे या बाजूने आपला force apply करायचा. So applying force in this direction. पाहिजे त्याला नाव द्या. This is A, B, C, D. I am calling this to be, this is F, force F. This is A, then this is B, C and D. Similarly, I am giving here to be E, F, G and H. These are the names given to this. This is the cube shown here. Now this cube is pushed from the upper side. वरची side फक्त त्याला force ने apply केलाय, force capital F. I am writing this to be capital F, and this is area. तर याचा area जो असेल, so I am taking this to be small a is the area of this particular upper face. When it is pushed, what will happen? Every याच्यातली प्रत्येक layer थोडीशी पुढे जाईल, and this layer will be at fixed. So you will get a new cube will be as shown by this. आपण dotted ने दाखवूया. So this will get shifted towards this. The next shifting will be observed. So this is called as याला आपण shear म्हणतो. So this is called as shearing. So the पत्त्याचा कॅट जो असतो, पत्त्याचा कॅटचा तुम्ही खाली फिक्स ठेवला हात आणि वरतून जर थोडासा वरची लेअर डिस्प्लेस केली, you will get this type of displacement as shown by this. Okay, so this cube will get sheared as shown by this, and here this angle is theta. This is called as shearing angle. So there is some deformation. त्याच्या साइज मध्ये किंवा शेप मध्ये थोडासा डिफॉर्मेशन होते, and this is the diagram that shows you there happens something shown as per this diagram. So this is theta in both the cases. This angle, shearing angle, is said to be theta. So this upper layer gets displaced by some maximum displacement, आणि याला तर मी नाव देतो. This is A dash, this is E dash, this is F dash, and this is B dash. Okay, so these new locations will be A dash, B dash, C dash, E dash, B dash, F dash and E dash. So that is my new face of that particular cube when it is in the deformed position. Okay, now draw this diagram and we'll write something about this. So consider a cube, okay, A, B, C, D, E, F, G, H. This is the 8 corners of this. The lower face.
डायग्राम ड्रॉ करायची
हो काढा, किंवा नका असेल तर नका काढू, काही गरज नाही. इतक्या काढा की. शॅल आय गिव्ह सम टाइम, काही वेळ देऊ? ओके, मी इकडे लिहितो, तुम्ही डायग्राम पण काढा आणि लिहा. आपण विल डिस्कस दिस. Consider a cube A B C D E F G H. The lower face is fixed, and lower face is fixed, and a tangential 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 force. Okay, tangential चा अर्थ लक्षात घ्या. It is along one of the face, एका फेसच्या डिरेक्शन मध्ये, जसं आपण डोक्यावर हात फिरवतो, दिस इज टँजेन्शियल मुवमेंट. तसंच इथं सुद्धा दिस फोर्स इज अप्लाइड इन केस only on the upper surface. Okay, so that is what we are discussing here. So this is called as tangential force applied over the face ABEF, the face ABEF of area small a, ABEF of area small a. It gets displaced, to the position A dash, B dash, E dash, F dash, F dash, E dash. You can write this, whatever. A dash, E dash, F dash is like that. Okay. Now, आता प्रत्येक लेयर, आपण जर समजा ह्या लेयर असूम केलं तर प्रत्येक लेयर गेट्स डिस्प्लेस्ड, but the angle here is going to be theta. So we can say this here, this each horizontal layer of the cube, सगळ्यात जास्त वरच्या लेयरचं असेल, सगळ्यात कमी खालच्या लेयरचं डिस्प्लेसमेंट असेल. त्यामुळे each horizontal layer of the cube then gets displaced. प्रत्येकाची थोडी डिस्प्लेसमेंट, and comma, the displacement is proportional. To the distance from the fixed plane. म्हणजे ह्या खालच्या प्लेन पासून जितकी वरती तो लेयर असेल तेवढं त्याचं जास्त डिस्प्लेसमेंट असेल, जितक्या जवळ असेल त्याचं डिस्प्लेसमेंट कमी असेल. अँड देअरफॉर शिअरिंग स्ट्रेन, SHEARING, शिअरिंग स्ट्रेन is given by displacement of a plane, of layer or plane, divided by distance from the fixed plane. कुठल्या बाजूला, म्हणजे किती त्याचं डिस्प्लेसमेंट आहे आणि किती त्याची डिस्टन्स आहे फ्रॉम द फिक्स प्लेन, that will decide the shearing strain. And therefore for the last phase, this where we have applied this force, this is given by, here it shows A dash is the displacement. Okay, A dash, I'll write once again, this is equal to A dash, this is the displacement shown here, या diagram मध्ये दाखवले, this is the displacement, and this is L, distance from the fixed face is this is AD, A and D, AD, this distance AD. So therefore I can write this is equal to small l upon capital L. I am taking this A dash is equal to small l here, displacement. And as we know, in case of triangle, this side, okay, this side, tan theta is equal to this upon this. Okay, if this is I am drawing this like this, this is theta, this is my displacement L, and this is capital L. We can get, this is nothing but tan theta. So shearing strain is equal to tan theta. And remember, in case of solids, this displacement is very small as compared to its length, therefore tan theta is very small. Okay, when theta is very small, tan theta is approximately equal to theta. आता बऱ्याच जणांना 12वी मध्ये हे अप्रॉक्सिमेशन माहित नसेल. गो फॉर डिफरंट व्हॅल्यूज ऑफ tan 0. 0 पासून सुरुवात करा, 0 आणि 1 डिग्री पर्यंत. You will find that value of tan theta and angle itself are approximately equal. We are using this approximation here, and therefore we can write very straight relationship. Shearing strain is given by simply theta, the displacement angle. Shearing strain is given by simply theta.
रेग्युलर मॉड्युलस ऑफ रिजिडिटीचं एखादं ऍप्लिकेशन सांगू शकता का तुम्ही?
ओके मला आवाज नाही आला तुझा व्यवस्थित.
रेग्युलर यूज मधलं मॉड्युलस ऑफ रिजिडिटीचं एखादं ऍप्लिकेशन सांगू शकता का?
खूप ऍप्लिकेशन्स, तेच मी सांगितलं की आपल्याला सेपरेट एक लेक्चर घ्यायचं आहे, ऑल ऍप्लिकेशन्स ऑफ बल्क मॉड्युलस, रिजिडिटी मॉड्युलस एक्सेट्रा. म्हणजे एक ऍप्लिकेशन सांगण्यापेक्षा तेच मी सांगितलं.
सॉलिड मध्ये येणार ना?
नाही, एक तुझ्याकडे समोर जे टेबल असेल ते टेबल फक्त वरच्या बाजूने थोडंसं प्रेस करायचा प्रयत्न करा. व्हॉट विल हॅपन, आपल्याला ते कळणार नाही, बट सम ऑफ द ऍटलिस्ट म्हणजे ॲटॉमिक लेवलला तरी काही ॲटम्स हे पुढे सरकतील, ठीक आहे. सो दॅट चेंज इन व्हेरी व्हेरी स्मॉल. सो मग त्याच्यामध्ये शिअरिंग स्ट्रेस किती आहे, शिअरिंग स्ट्रेन म्हणजे त्याचं त्या मटेरियलचा हा तिसरा मॉड्युलस किती आहे, डिपेंडिंग अपॉन दॅट पर्टिक्युलर थिंग विल गेट डिस्प्लेस्ड. ऑन द अदर हँड जशी मी सांगितल्याबरोबर तुम्ही पत्त्याचा कॅट घेतला आणि तो कॅट जर वरच्या बाजूने त्याला फोर्स अप्लाय केला तर खूप डिस्प्लेसमेंट तुम्हाला दिसेल. सो दिस इज वन व्हेरी इम्पॉर्टंट प्रॉपर्टी ऑफ मटेरियल्स. अर्थात हे काही मटेरियल नाही, म्हणजे पत्त्याचा हे काही मटेरियल नाही, बट इन केस ऑफ मेटल देर आर सेव्हरल डिफरंट टाइप्स ऑफ मटेरियल्स which are having good shearing stress or shearing property, and that's why there are several applications. खूप मेकॅनिकल मशीन्स मध्ये several there are machines, mechanical machines where this type of property has been used. Okay, usually in construction मध्ये खूप वेगळ्या प्रकारच्या construction मध्ये किंवा वेगळ्या machines designs मध्ये this property has large applications. So all these applications we will discuss in detail when we go for actual this applications of elasticity. That is the last part of our topic. Okay, we'll discuss clearly, don't worry about this. Now let's go further. So therefore now modulus of rigidity. Okay, this eta is given by tangential stress divided by shearing strain. Okay, shearing strain. Remember, this is bit different. म्हणजे पहिल्या दोन्ही पेक्षा याची डेफिनेशन थोडीशी वेगळी आहे, त्यामुळे आपल्याला थोडासा त्याच्यामध्ये चेंज येऊ शकतो. सो दिस इज F अपॉन स्मॉल a, फोर्स अप्लाइड अपॉन एरिया ऑफ दॅट फेस इज A, डिवाइड बाय थीटा, और this is also given by eta is equal to, so this is capital T upon T is tension divided by small theta. Okay, so here we can write this. T is tangential force applied per unit area. Tangential force applied per unit area. This is applied per unit area. Okay, आता इथं सुद्धा फोर्स पर युनिट. नाव थीटा इज अ नंबर, जरी तो रेडियन्स असला तरी तिथले त्याचे डायमेन्शन्स आपल्याला फारसा तो नंबर असेल. सो वी आर नीड नॉट वरी अबाउट. सो दिस इज अगेन ए टेन्साईल स्ट्रेस. किती डायमेन्शन्स आणि त्याचे युनिट हे टेन्साईल स्ट्रेस सारखेच असतील. सो राईट हियर युनिट्स अँड डायमेन्शन्स ऑफ eta, okay, modulus of rigidity, are those of stress or pressure. Okay, now look, in examination असं तुम्हाला विचारू शकतात, it is true or false, units and dimensions of eta are those of pressure. So it is true or false? It is true. So that's why we have this, that's why we are writing each and every statement here, because very many times in examination very simple question is asked over this. So pressure and modulus rigidity have same dimensions and units, true or false, or काही options आपल्याला दिले असतात. So units and dimensions of eta are those of strain, pressure, then force, then displacement, etc. So you have to select a particular answer from that. So that type of questions may be asked like this. Okay, and most important thing here, like जसं आपण मगाशी बघितलं की यंग्स मॉड्युलस इज ॲप्लिकेबल फॉर सॉलिड्स ओनली, bulk modulus is applicable for solids, liquids and gases. Now this modulus of rigidity is also applicable to solids only. So right here, like Young's modulus, comma, modulus of rigidity, eta is possessed by solids only. Okay, so liquids and gases do not have definite shape of their own. त्याचे स्वतःचा शेप असू शकत नाही, त्यामुळे त्या केसमध्ये आपल्याला हा मॉड्युलस ऑफ रिजिडिटी काढता येत नाही. ओके, सो जस्ट इन शॉर्ट विल राइट solids, liquids and gases. Okay, so there is y, there is this k as well as eta. There is only k and this also has only k. So this is modulus. These are the modulus, three modulus. This is applicable for solids only, and for liquids this is only k, for gases also only k. So this is a small table that tells you what are the different types of materials exist in nature and what are the three different types of modulus or constants applicable here. And that's why you will find that when we go for application, जेव्हा आपण application ला जाऊ त्यावेळेस आपल्याला ह्या सगळ्या गोष्टी माहित असणं अत्यंत आवश्यक आहे. So all these three constants are applicable to solids, whereas for liquids and gases only second modulus, that is bulk modulus, is applicable. It has large many applications in thermodynamics and other branches of physics too. Okay, now this is what a very primary discussions about this. There is another important derivation, but that will again require one more lecture. We will cover that derivation in the next lecture. Okay, today let's go for another example. एक छोटासा example घेऊया and then we'll stop here. Example for this Young's modulus. Example 1. First example today. Right here statement: a load of 4 kg is suspended from ceiling. Sorry, just a minute. A load of 4 kg is suspended from a ceiling, ceiling म्हणजे छत, ceiling, through a steel wire of length 20 meters and radius 2 millimeters. Okay, so see this, MKS, CGS, etc. It is found that the length of wire increases by number is given to be 0.031 millimeter. Okay, इथं तुमचं कन्वर्जन म्हणजे how you are expert in CGS MKS, that would be decided by this problem. Find Young's modulus of steel, and here take value of G is equal to 9.8 meters per second square. So first decide whether do you have to solve this problem in CGS system or MKS system, but most of the units are given in MKS, so we'll convert everything in MKS. Now let's see what are the given. Okay, so first it is mass is given to be 4 kg. Second, total length is given to be 20 meters. Radius is given to be 2 millimeters, and we know that millimeter is 10 raised to minus 3 meters. So it is 2 into 10 raised to minus 3 meters. So 1 millimeter is 10 raised to minus 3 meters, and the length is given to be okay, this is 0.31, sorry, not 31 millimeters, means 0.31 into 10 raised to minus 3. So I can write this to be 3.1, and these two digits 10 raised to minus 3, so it becomes 10 raised to minus 5 meters. Now these are the numbers I am given. Now first calculate longitudinal stress. Or you can directly write that formula too. So it is given by capital F upon A. So F is mass into acceleration, N into G. So this is what? This is the ceiling. Wire of 20 meter is used. Some weight is attached here. Okay, this is the weight has been attached, and because of this length changes. So, and therefore this is mass, this is 4 kg, and G, that is Earth's gravitational constant, acts over this. This becomes a force here. So this is mg. Divided by A is pi into r square, that is cross section area of this wire. Whatever this. So it gives you 4 into 9.8 meters per second square is that. Then this is 3.14 into 2 into 10 raised to minus 3 square.
Area pi square.
Radius is given, pi r square. Cross section area is given, correct? What is the problem? Length नंतर stress मध्ये येईल ना, strain मध्ये येईल. Longitudinal stress is force per unit cross sectional area. Cross sectional area is given by pi r square. And if this calculation is done, this is 4 in, now this is 2 square. So this will be 4. This 4 will get cancelled. 10 raised to minus 6 becomes 10 raised to minus 3 becomes 10 raised to minus 6. So that can be taken in the numerator. So it is 10 raised to 6. 4 gets cancelled. 9.8 upon 3.14. This is approximately, if it is calculated, it comes to be 3.1. Okay, newtons per meter square. This is the dimensions of this longitudinal stress. Now longitudinal strain. Strain, that is given by small l upon capital L. Simple. This is going to be a number. So these numbers are given. 3.1 into 10 raised to minus 5 meters divided by original length is 20 meters. So if this one of this 10 raised to minus 6 होईल, and 3.1 divided by 2 comes to be 1.55 into 10 raised to minus 6 meters. पुस्तकामध्ये चूक आहे. पुस्तकातल्या एक्झाम्पल मध्ये थोडीशी चूक आहे. सो ट्राय टू अंडरस्टँड दिस. सो 1.55 into 10 raised to minus 6 meters. Okay, this is 10 raised to minus 1, 10 raised to plus 1 taken in numerator, it becomes 10 raised to minus 1. So minus 5 minus 1 is minus 6, and 3.1 upon 2 is 1.55 naturally, and therefore calculate y. Therefore y is equal to stress upon strain. Replace the numbers. Just 1 or 2 minutes will finish this. 3.1 into 10 raised to 6 divided by, this is also 3.1 into, sorry, 1.55 into 10 raised to minus 6. So taking this here again become plus. This is exactly double of this. So it is 2 into 10 raised to 12 newtons per meter square. This is my final answer. 2 into 10 raised to 12 newtons per meter square. In our book, textbook, there is a mistake. They have given 20 meters, and in actual problem they have taken 2 meters is the length of the wire. So म्हणजे तुम्ही जे काही लेंथ घ्याल त्याप्रमाणे हा थोडा नंबर बदलेल. ओके, सो हियर we'll today stop here. In the next lecture tomorrow we'll go for remaining problems of this topic. Okay, just